All right, so we're going to do some differentiation rules, working on expanding what we know about the derivatives of e to the x and exponential functions, I should say, so various bases to the exponent x. So based on what we know from what the derivative of e to the x is and b to the x, can somebody help us with the warm-up question from part A? What's the derivative of f at x? Michael?
Oh, the derivative. Never mind.
Yep.
Solve for x.
Okay. Derivative of f at x? Kaylee? 4e to the x, yep. So constant multiple rule means that the 4 stays, and then we know the derivative of e to the x is e to the x. Where does the negative 3 go? It's a constant, so the derivative's 0. Yep, so that's gone. Okay, derivative of g to the x. Is anyone able to help us with this one? Kaylee? Awesome. So the derivative of exponential functions is ln of the base times the exponential function. So we get the function back and then times the ln of whatever that base is there. That's also the reason why e to the x is the derivative of e to the x, because if we multiply by ln e is just 1. Okay. So we are going to practice kind of bringing in some previous rules that we've learned in the course into exponentials, derivatives of exponentials. What was that?
That was my textbook.
Oh, wow, that was very loud. Is everyone awake now? No? Okay. All right, so for the first one here, we're going to think about this as product rule. So we need to do derivative of the first, which is derivative of x. So 1 times the second plus the first times the derivative of the second. So you're going to do e to the x. So if we common factor here, we'll be left with e to the x times 1 plus x. Okay, so we're applying product rule for this first one. Any thoughts on what the derivative of part B would be equal to based on what you know about previous derivatives? Okay, so with the derivative of e to the x, we know we get back the function itself, so we'll get back the exact same thing. And then Anita is suggesting that this is times 2. Where does that come from? Why does she say that?
That makes sense.
Makes sense? Why? Yes, so we have to do like the derivative of the exponent. So it's like exponent prime here. So we usually write coefficients out front. So proper way to write this would just be 2 e to the 2x plus 1. Pardon? You will always multiply by the derivative of the exponent, but you will also multiply if this was something like 3 to the whatever exponent, you'd also have to multiply by ln 3, just like we did up here. So when your base is anything other than e, the derivative of the exponential is the base back times the ln of the base times the derivative of any exponent. Okay? All right. So we're kind of doing like a chain rule thing here where we also have to multiply by, just like we do with trig functions, we multiply by the derivative of the inside. Here we have to multiply by the derivative of the exponent. Okay, perfect. Anyone want to give C a try? Okay, so Grayson says possibly the exact same thing. Do you guys agree? So the derivative is this? Okay, so we also have to multiply by the derivative of the exponent, right? So this needs to be multiplied by the derivative of negative x, which is negative 1. So we'll get e to the x plus e to the negative x. Okay, so you need to multiply by the derivative of the exponent. Okay, here we're going to apply product rule, so bringing in some trig stuff as well here. So derivative of the first is basically just itself, times the second, plus the first times the derivative of the second. It's negative sine x. Okay, so if we common factor here, we can take out a 2e to the x. We're left with cos x minus sine x. Oops. Hey, any questions on this one? Okay, we're also going to apply product rule here. We have x squared times 10 to the x. So derivative of the first is 2x times the second, which will be 10 to the x, plus the first, just as it is, times the derivative of the second. What's the derivative of 10 to the exponent x? Ln 10 times 10 to the x. Okay, so we can common factor out a 10 to the x here. Oh, and we can also factor out an x. And then we're going to be left with 2 plus ln 10 times x. Just spelled rule wrong. Hey, can I clarify anything here?
Oh, Mr. Gillis, I just want to know if we could look at that step there. So how do we know when we're done?
So the question was, how do we know when we're done? I would say, like, once you've applied the rule, you're just going to check to see if things can be factored or common factored. And then if you're working with trig functions, you can see if you can potentially simplify using some trig identities.
Or other than that, just take the calculus and then just write down what we get.
Yeah. Okay, so I guess like a good check would be like, is it fully common factored once I've done like the derivative stuff? And then with trig functions, are there any identities I can sub in here? Okay, any other questions for these? Derek, did you have a question?
Could you put like the x in front of
Yeah, usually we put coefficients like numbers in front of x, which is why I did that, but x ln 10 is fine as well. Yeah. Anything else, Nicole? No? Okay. No worries, no worries.
Why are you stressing your test is done?
Okay, identify the local extrema of the function f at x. Okay, so let's think back to unit 2 here. How do we go about finding local extrema and identifying them? What do we have to do?
First derivative test.
Okay, so we need to do first derivative test. I mean, we could also do second derivative test, but we will have to do maybe some kind of table if we do the first derivative test. So let's find the first derivative. We're going to do product rule here. So derivative of the first time, or did I do one from this above? Oh, we did something very similar. Derivative of the first times the second plus the first times derivative of the second. So we'll get e to the 2x back, but we also need to multiply by the derivative of the exponent. So derivative of 2x is 2. Okay, in order to find critical numbers, we need to set our first derivative equal to 0 and solve for where that happens. So in these cases especially, it's going to be important to common factor because you kind of need to solve for like the individual pieces of the function. So we're going to have 1 plus 2x here. Okay, so Grayson just mentioned that e to the 2x actually cannot equal 0. Why is that? Pardon, essay? So e to the power 0 still equals 1. Also exponential functions, if they're not like shifted up or down at all, which in this case, this is just an exponential function that has like a horizontal compression. They all have horizontal asymptotes along y equals 0. So this function kind of looks like it has a horizontal asymptote along the x-axis, and then it kind of looks like this, right? So this function is never going to be equal to 0. There's no x for where we would get a y equal to 0. So that's not going to happen. But we do have a solution to this. Where is 1 plus 2x equal to 0? Negative what? Negative half, yeah. And if you're not sure, go ahead and set it equal to 0 and solve for x, right? When we do that, we should get negative 1 over 2. Okay, so this is a critical number. Yep, so if we're going to do first derivative test, we're going to do a little sign chart here. And we're going to plug it into f at x and make some observations about, or we're going to plug it into f prime at x and make some observations about f at x. Okay, so if we plug in negative 2 in for our derivative function, we're going to get a negative 3 inside the bracket, and then e to the negative 4 is just like a small decimal. So here we'll get negative, which means that f at x is decreasing. And then when you plug in 0 here, we know that this becomes 1, and this becomes 1. So 1 times 1, that's a positive value. That means f at x is increasing. So we have a local min. And because we're identifying local extrema, this is usually like an xy coordinate. So we're just going to evaluate f at negative half. So just subbing it into the original function here. So that's just going to give us negative half e to the negative 1. So we can write that as negative 1 over 2e. Okay, so I'm just here applying the negative exponent rule, which says if you have a negative exponent, you can make it positive by moving it to the opposite side of the fraction. So here, this just equals negative 1, and then apply negative exponent rule, move it down, make the exponent positive. Okay, so we have a local min at the point negative half, negative 1 over 2e. Vectors is different. There's a lot less like algebra, I would say.
Let's go.
Okay, any questions on this one? Can I clarify anything? Yes, A.
All the physics of the day.
So we're just plugging it in here. If you plug that into your calculator, you'll get just like a decimal, a positive decimal from this part, and then this will give you negative 3. So positive times negative gives us negative. Okay, let's continue. Guys, put the phones away, please. Okay, we're going to take a look at an application here.
Oh, there's more application.
So the effectiveness of studying for an exam depends on how many hours the student studies. Some experiments show that if the effectiveness, capital E, is put on a scale from 0 to 10, then we have an equation E at T, where T is the number of hours spent studying for an examination, and E is our effectiveness on a scale from 0 to 10. So if the student has up to 0 hours for studying, how many hours are needed for maximum effectiveness? So it doesn't necessarily mean if I study the full 30 hours that I'm going to reach maximum effectiveness. After a certain point, this is basically saying that the effectiveness will kind of dip, potentially. Pardon? So what are the options for studying here? What are my endpoints? The student has up to 30 hours to study, so they can't study more than 30 hours. What's the other low-end option? They could not study, yes. So we know that t needs to be between 0 and 30. It's always good to test our endpoints in our function along with any critical numbers because the endpoints could be maximums or minimums. So we'll need to check if either of those two are maximums. Okay, we also need to find the derivative to find critical numbers. So before we find the derivative, I'm actually just going to put the 0.5 into the function so that we don't have to worry about the constant multiple in front. So oh, sorry, I missed the E. Okay, so finding the derivative here. The derivative of 5 is 0.
Hold on, Mr. Taylor.
Yep.
How did you get 5 plus 0.5? Wait, where'd the 5 come from?
I'm bringing the 0.5 inside the equation here. Okay, for this part, we're going to apply product rule. So we're going to get derivative of the first, which is 0.5, times the second, just as it is, plus the first times the derivative of the second. So when we do the derivative of e to anything, we'll get back that value. But then we also have to multiply by the derivative of the exponent. So what's the derivative of our exponent here? Yes, negative 1 over 20. All right, and in order to find critical numbers, we need to know where this is equal to 0, right? So we're going to set that equal to 0. So I'm just going to clean this up just like a tiny bit. When I do 0.5 times negative 1 over 20, I get negative 1 over 40, or if you want, you can write it as 0.025.
How come you don't want to factor something out here?
I am going to. I'm just simplifying these numbers first. Okay, so if we factored out 0.5 here, which we could, and then also e to the negative t over 20, that might be easier for us to solve. So we'll be left with 1 here, which makes it a bit easier, and then we'll be left with negative 0.05 t. Yeah, when you do 0.025 divided by 0.5, because you're common factoring, you get 0.05. Okay, so this part of the equation, is this ever going to equal 0? Okay, basically we just have a function that's now like below the x-axis, so there's still an asymptote here, and then it's, oh, I guess it's actually more like this. Okay, so this is never going to equal 0. There's an asymptote there. This could equal 0, though.
Is there ever a case where it would?
If you had something like plus 1 here, that shifts the whole graph up 1. That can equal 0.
But if there's a multiple in front, it would just like stretch it.
Yeah, exactly. Okay, so what do we get here? I think we get 20. Yeah?
Yeah.
Okay, and time here is number of hours, so this is hours. Okay, here's a critical number. Okay, I don't really need to know whether this is a local max or a local min. We're finding like absolute extrema. Grayston, shh, whisper at least, okay? We're finding absolute extrema here, so what is the absolute number of hours that will give us maximum effectiveness? So absolute maximum. So we are going to test endpoints and critical numbers. So you're going to evaluate E at 0, E at 20, and E at 30. These are going to give us the effectiveness of that hour, number of hours of studying along the scale from 0 to 10. So we're subbing this into our original function up here. So take a second and do that.
Can we just do decimals?
Yep, decimals are fine. Okay, really we're just interested in which one is going to give us the highest number. So. Okay, so E at 0. What does E at 0 give you? 5. Anyone have E at 20? 8.35. Anyone else find E at 20? Come on, guys. Use your calculators.
I would be doing it, but I left my calculator off.
So use your mental.
Oh, sorry, 20 and 8.6. Yeah.
Oh, 8.68. And that was E at 30?
Yeah.
8.35. Okay, so, shh, guys. So how many hours is going to produce maximum effectiveness?
20 hours.
Okay, perfect. Great. Yeah. Okay. Like mic drop, pencil drop. Got you.